Hi, my name is Faisal Chaudhry, and this lab presentation is about observing the motion of a star orbiting a black hole of an unknown mass. The observation of the star's motion will be conducted through a computer model in GlowScript that will generate a unique star trajectory linked to my student email. The goal of this lab is to analyze the net force on the star at each data point of its movement as it travels around the black hole. Through analyzing the net force and its parallel and perpendicular components on the star, an estimation of the black hole's unknown mass can be made using Newton's second law, also known as the momentum principle. Before I discuss the fundamental principles I used in the lab, I wanted to include some assumptions that were made. Firstly, the net force acting on the star is due to a single force, which is the gravitational pull of the black hole located at the origin. Also, the star has a predetermined mass of 2 times 10 to the 30 kilograms. Furthermore, since I am using the observed star position versus time data to estimate the mass of the black hole, there will be multiple estimations of the mass since the net force is changing in the star's orbit. Therefore, there will be issues in determining a precise mass of the black hole, so an estimation of the average masses found will have to suffice. The fundamental principles that I use to explain and analyze my findings are Newton's second law, or the momentum principle, and Newton's universal law of gravitation. For Newton's second law, I express the quantities in terms of momentum, so the change in the star's momentum is equal to the mass of the star times the change of the velocity of the star. Through that, the rate of change of momentum is equal to the net force acting on the star, which plays into the universal law of gravitation, shown here. The universal gravitational constant is multiplied by both the mass of the star and the mass of the black hole, and then divided by the distance between the star and black hole squared. Also, since I am analyzing the parallel and perpendicular components of the net force on the star, the sum of the rate of change of momentum in both the parallel and perpendicular direction will equal the net force on the star. Using the fundamental principles, I edited the starter GlowScript code to analyze the net force on a star as it orbits the black hole in a unique trajectory. The unique trajectory was generated with using a pre-coded path, so I edited the initial constants in time loop to reflect what I was given initially. I had the star mass of 2 times 10 to the 30 kilograms, and the delta t was a day, or 60 seconds times 60 minutes times 24 hours in a day to reflect a day in seconds. The while time loop iterates over each data point determined by the index, which gives the x and y components of the star velocity in terms of a vector. I added the formulas based on the fundamental principles to determine the net force across each data point on the star's movement. Using these formulas, I was able to express the universal law of gravitation in terms of the unknown mass of the black hole so that I can estimate it in the model. The model generated an estimated mass for each data point, so I found the average of all of the estimated masses of the black hole using Excel. The estimated mass of the black hole that I found is ultimately 9.07 times 10 to the 33 kilograms. For the net force and the parallel and perpendicular arrows, I made the arrow scale a very small number for visual clarity, and you can see the net force components changing as a star moves around the black hole. The magnitudes of the net force as well as the parallel and perpendicular components are printed below the model. So for the what does it mean question, it is basically asking if or how the net force and its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. From my discussion of the fundamental principles, it was already stated that the rate of change of momentum is equal to the net force acting on the star based on the momentum principle. Therefore, since the rate of change of momentum equals the net force, then its parallel and perpendicular components will each equal the net force's parallel and perpendicular components respectively. I modeled that in the GlowScript code, so the model was able to accurately generate an approximate magnitude of the net force acting on the star through the inclusion of the star's momentum changes. To answer the what if question, since the motion of the star remains unchanged in terms of its position and velocity vectors, it would technically be impossible to estimate a new mass of the black hole that would be different from the original estimation. Using the universal law of gravitation expressed in terms of mass of the black hole, all the values in the formula would be the same as the original ones. The net force is still only the gravitational pull of the black hole, and the black hole is still at the origin, so the distance between the star and the black hole will remain unchanged. G is a universal constant, so if the star's motion remains unchanged, then the estimated mass of the black hole will be this as it was before. The only way the black hole mass could change is if we assume a different star mass. But if we are not changing the star's motion, then the estimated mass of the black hole will be the same as the original one. So in conclusion, the star's motion is only being affected by a net force, which is the gravitational pull of the black hole at the origin. Using the momentum principle and Newton's universal law of gravitation, the mass of the black hole can be estimated through analyzing the star's orbit.